Oh, we we can choose to increase the laser power so that are removing hundreds of nanometers up to, a micron of material per layer, or we can decrease the power so that we're removing just tens of nanometers. So we can create
Cara
high
meningkat
resolution depth
untuk
profile.
pengusulan
Yep.
angka kredit promosi dapat kami jabarkan sebagai berikut bahwa dari dosen nanti pada semester ada mengumpulkan angka kredit promosi
Sorry, was that a question or
bila
just someone with
melakukan
background noise?
karya
Oh, no, I
dan
think somebody just forgot to
Okay,
turn
no
off
worries.
the mic, yes. Just go
No
ahead.
worries.
Yeah.
Okay, great. Yeah, so back onto the depth profiling. So we have experience doing depth profiles through tens to hundreds of nanometers, as well as very high resolution, tens of microns of material, as well as very high resolution, tens of nanometers depth profile. So for the next part of the presentation, I will just go through some application examples that show these modalities and show the technique's capabilities. These are mostly, geoscience focused and address some of the questions that I know you had before the presentation. So the first one that I'll go through is trace element analysis of gemstones. Oh, sorry, I didn't realize that my video had stopped. Sorry about that. Um, so you can see on the right here, this is an example of our sample holder. So we can fit anything within a 90 millimeter by 90 millimeter area. Again, this offers a lot of versatility for solid materials. For this particular example, we're analyzing about 25 gemstones. We can analyze up to 30 samples of this size. And again, there's also custom sample holders available if you have smaller samples and would like a higher throughput sample analysis tray. But you could also choose to analyze like half a core, for example. So we can analyze very large samples in this area as well. But what you're looking at here was a study on some gemstones, which many of you may be familiar that the trace elements in gemstones can determine whether they are natural or synthetic, or it can determine which countries they came from. And this is very important for the gemstone trading industry. But obviously, we don't want to digest our gemstones in acid and lose their value. So it can be very challenging to get trace elemental analysis in a non-destructive way. And what we proved with this study is that we can take just a 5 micron laser spot size and see the trace elements that we need in order to determine, is this is this gemstone natural or synthetic, and where did it come from? So what you're looking at on this screen, this is an example of some of our mass spectrum that came from a corundum, which is the mineral that is used to make rubies and sapphires. A corundum reference material with known concentrations of these elements in the parts per million levels. And what I really want to point out is this beryllium peak here that is at a known concentration of 3 parts per million. And you can see that we easily detected it. And again, advantage that we're able to analyze those light elements that are very important in determining the origin of these gemstones. So we can get trace level detection even with very small laser spot sizes. And a lot of LA-ICP-MS techniques for this type of gemology work need to use 25 to 40 micron spot sizes, so larger spot sizes. So now we'll go through some quantitative application examples. And the first example that I'm showing here is our analysis of this set of mineral powder micro standards that come in a lithium exploration kit. So you can see that there are several different types of mineralogies included in the sediment standards. And what we're doing here is we're plotting the peak intensity of lithium against the known concentration for each of these different samples. And the different data points are just different replicates on an individual sample. And what you see is a very linear response from parts per million level lithium all the way up to over 2.5 weight percent level lithium. So this is how we would create a multi-point calibration curve anytime we are not sure about the mineralogy or the matrix of a given material. We could use a set of reference materials like this that create a linear calibration curve across a range of concentrations, and then we would see where our unknown plotted along this line and would be able to determine the concentration of lithium. So this is similar to what you would do with an XRF or LA-ICP-MS, finding solid reference materials that have known concentrations of elements is how we calibrate and how we determine the concentration of any unknown sample. Now, we can also do single point calibrations. So anytime we have a matrix matched reference material where we can just use one reference point and just draw a single calibration from that one point, that is another option for doing quantitative analysis. And in this example, we analyzed a black glass reference material. You may be familiar with glass reference materials because they have so many different elements in them. They are great for quantifying geologic samples, and they're used a lot in LA-ICP-MS as well. But what we're showing here is our ability to treat one of those black glass reference materials as an unknown, use another black glass reference material as the calibrant, and accurately quantify all of these elements from the major elements in weight percent to the minor and trace elements in parts per million. And I know you all are quite focused on rare earth elements, so you can see how we are accurately quantifying the rare earth elements as well. The blue bars are what our technique quantified, and then the gray bars are the certified values of that reference material. So we're validating that we are getting accurate results when we use a single point reference material of a black glass, and verifying that we can accurately quantify all of these elements, everything from lithium all the way up to uranium, including the rare earth elements at parts per million levels. So now I will move on to a few mapping examples. So this is looking at our elemental mapping for different mineralogies in a polished block sample. So you can see this polished block here on the left that is primarily made up of some sphalerite, galena, and then what the customer was especially interested in is where are those gold-rich phases in this sample. So what we did was analyze I believe it was 26 by 26 millimeter elemental map across this sample. We did an 80 micron spot size. So what you're looking at here is every single one of those pixels is an 80 micron laser ablation spot size that has that full mass spectrum of data behind it. So when we look at a given elements or isotope, I should say, a given isotope's elemental map, where we see red and orange, those are relatively high concentrations of that element compared to the darker colors where they're relatively low. So each of these maps is relative to itself, and where we see relatively high amounts of lead, for example, that shows us where the galena phases are because lead is a major component of galena. And then where we see iron and copper and zinc, those are representative of the sphalerite. But what we were also able to identify is trace amounts of silver and gold that were below the detection limits from some of the other techniques that were used to analyze this sample. And so in particular, you can see this spot here with a high concentration of both gold and silver. And then you see a few other areas with high concentrations of gold that do not correspond with high concentrations of silver. So again, identifying where those gold-rich phases are and proving that this technique can detect gold at very low limits that other techniques could not. And so then what we can do is we can take an area like you see in this orange box here, and we can do another map at a smaller laser spot size and get a higher resolution understanding of the sample. So you can see this is a 4 mm by 4 mm elemental map with a 20 micron spot size. I should also point out the time required for these maps, where the time required is just based on how large of an area and how small of a spot size. But even acquiring these very high resolution maps of 4 mm only took about half an hour. So once again, we're looking at the copper, the zinc to show us where the sphalerite phases are, the lead and the sulfur to show us where the galena phases are. You can also see fluorine has some very distinct areas where it is high, suggesting a different mineralogy. And then in particular, once again, what the customer was looking for is where are those high concentrations of gold? And then you can start to look around using the other elements to determine what are the mineral hosts for these high areas of gold. So this can be a great tool for identifying any sort of trace elements that maybe an X-ray or a SEM-EDS tool fails to identify. And so then the last example, actually the second to last example that I'll go through is looking at some zircon grains. I know there was a question and some interest in could this technique be used to date or understand the age of rocks, rocks or zircon grains. Zircon grains are used a lot in geochronology to understand the age of certain materials. And you can see here, we analyzed two zircon grains with a 5 micron laser spot size, so getting a high resolution map of these two grains. What you're looking at here is the zircon map. So where you see those bright blues, that is high zircon. Where you see the darker blues, those are the outside of the grain where there is no zircon. But then you also see that these samples had been analyzed by a traditional LA-ICP-MS before we analyzed it. So you do see some of these spots here that are not related to any sort of chemical composition within the zircon grain. Those were caused by another laser ablation technique. But what we were able to detect here is 238, uranium-238, as well as uranium-235, which can be used for lead uranium dating. You can see in particular on the grain on the left that we have kind of this band where there's relatively high uranium compared to the relatively low uranium surrounding it. We see a little bit of a kind of a band on the other grain as well. So what this can be very useful for is doing this quick elemental mapping to identify where is the high uranium or the high lead to then send to maybe a higher precision tool so that you're able to very quickly target an area with high uranium and high lead in order to do a very high resolution geochronology analysis. So you see, for example, this laser spot, it did hit that area of high uranium, but these laser spots here did not. And so those might not have been very effective lead uranium dating analyses. So the mass boxes scan of this sample could have saved the high precision laser ablation ICP mass spec technique some time by identifying where specifically to target.
The doctor, he expected it to be a cyst or
You
something.
can also see the 206 lead and 207 lead that are used in this dating system.
Grab it.
Very interestingly, you see that the grain on the right, the high lead corresponds to where you see relatively high uranium, but in the grain on the left, we don't see that same trend. You see how there is a distinct area of high uranium, but the lead is more homogeneously distributed. So you can see that Massbox can pick up some discrepancies and some changes in isotope ratios. But as I'll talk about in the next application example, this is not a high precision isotope ratio tool. It is good for screening. It is good for some geochronology applications, but its isotope ratio analysis is approximately 1%, good for about 1%. And then the final map to point out here, again, because of your interest in rare earth elements, is that we did also detect lanthanum and cerium, some trace rare earth elements that were concentrated in some very distinct areas, kind of on the edges of the grains. So again, this technique can be effective at identifying those trace rare earth elements spatially, as well as determining their concentration in bulk, like we saw in the previous example. And so then the final application example is just to talk through that isotope ratio capabilities again. So this is, once again, another glass reference material. This is NIST standard reference material 610 that some of you may know if you are familiar with laser ablation, ICP-MS. And it has uranium concentration of about 460 parts per million. And you can see that we easily identified the major isotope of uranium, as well as when you zoom into U-235, we see that peak as well. So first, just to point out that, the U-235 peak would correspond to about 1 parts per million, and you can see that the peak is still well above our background noise. So we can analyze uranium at very low concentrations, which again is very effective in terms of screening and identifying where uranium is. But then we can also look at the ratio of these two isotopes. So you can see the ratio that we quantified on the left here compared to the expected ratio, which has been determined by other techniques and is published in literature. So in this sample, the uranium is depleted, so the ratio is non-natural, and we are able to measure that. But again, this technique is not an ultra high precision isotope ratio tool. Something like a multi-collector ICP-MS or MC ICP-MS or a TIMS is going to have much higher precision for very high precision isotope ratio and dating work, but you can see how the mass box can be a very fast and multi-element solution that can identify isotope ratios with pretty good precision, but this may not be suitable for all dating and geochronology applications, depending on what sort of precision is required. But as I was showing on this example, we have several customers who recognize that this is a tool that can provide screening and can identify where those high uranium and lead areas are that then can be passed along to an instrument that has that higher resolution isotope precision work. So then just to summarize here, and it seems I have left plenty of time for questions. So compared to the conventional workflows that combine laser ablation with mass spectrometry, this new technique that we've developed, LALI TOF MS, has some key advantages for geoscience applications. So specifically being able to get full quantification directly from any solid or powdered materials, everything from trace, parts per billion level up to bulk concentrations, even those light elements, lithium, carbon, nitrogen, oxygen, that are challenging with conventional spectroscopy technique. We can also do broad scale elemental mapping. So we showed examples of being able to do those large scale or millimeter scale elemental maps with micron level resolution to see how those elements change spatially within any solid materials. And I didn't show any examples, but I do have some examples in the backup slides if anyone wants to see what it looks like to get a full three-dimensional characterization, because we can just repeat that elemental mapping process and analyze multi-layered materials or understand how inclusions or failures might penetrate further in the subsurface. And then, as I mentioned, this is a high throughput and field deployable system. So unlike a traditional LA-ICP-MS that requires a lot of dedicated lab space, it requires an argon gas supply. Our system is just a compact benchtop design that can fit on a benchtop and just needs a power cable and temperature control. And then it also allows for very high throughput analyses. So as you saw, anything that fits within that 90 millimeter by 90 millimeter area can be analyzed and tested in the same analytical session as quickly as just a few minutes per sample. If you're just doing, a single spot in order to get a bulk composition, that can be done in just a few minutes. If you're doing a large elemental map, that may be on the order of half an hour to a couple of hours. You don't have the same tuning and plasma stabilization and transport delays that the conventional laser ablation plus ICP mass spec techniques have. So with that, I would love to hear what questions you all have.
All right. Thanks very much, Ellen. It's really
Thank you.
interesting. Because I personally ever used TOF MS last time,
Mhm.
a long time ago. But yeah, this one is new for me. LALI is
Mhm.
something new for me. It's laser ablation. Okay, I'm open for a question for anybody. You can just unmute and ask directly to Ellen, or can type your question in chat box. Or maybe okay, this question here from
Okay, so
Lemigas.
do you have any scientific papers that use Massbox to estimate zircon age or other isotope ratio analyses? So no, we don't yet have any scientific papers. As you saw in the zircon study, this was very much a proof of concept study for a university that was working on some zircon dating. And there is more work to do to validate what sort of isotope ratio precision we can get on these types of samples. I guess the other thing that I should point out is we have just recently released our next generation of our instrument. So this new generation came out just a couple of months ago. And so we are in the process of analyzing, all of these solid materials that our customers care about on this new generation and, verifying that it does in fact have greater sensitivity, ability to analyze different materials in a better way and get higher sensitivity at smaller spot sizes. So that's definitely on our list of things to determine is what sort of, lead and uranium isotope ratios can we get in the zircon dating for zircon dating analyses, but no published papers yet. And then what are the consumables that we need to consider while using MassBox? So that is a big advantage that it has much fewer consumables than your traditional ICP mass specs. So if you, I guess some of it depends on the sample preparation. So I will show this slide as well. So you may choose to do a hot press mount if you have like irregular shapes, or this also works well for geologic materials. So we also, if you're analyzing powders, we suggest they're pressed either with a hydraulic press or mounted in some way. So, you may have some kind of consumables from these sample preparation techniques. The other major consumable is we have this sacrificial glass window that protects the optic systems from the laser penetrating it. That typically needs to be replaced every year, but that is a very minor cost. And all of those sort of consumables that are associated with the instrument are included in a service contract. So we do recommend that our customers purchase a service contract. The first year the system is under warranty, and then after that, we suggest doing a service contract that then will allow the sacrificial glass window, any refurbishments or repairs on the lasers. We have not, I guess I should point that out as well. We've never hit the end of our laser life. These lasers are rated to, thousands, hundreds of thousands of hours of runtime. So we have not actually, hit the end of the life of the laser. The lasers are not, a high turnover, high consumable part, but we have had to do a refurbishment on some of our laser systems. So that would all get covered in a service contract. So besides the service contract and besides any sort of sample prep equipment, there's essentially no consumables and minimal operating costs, again, because you don't have the argon gas. It's a good question.
All right, thank you, Ellen. Let me speak in bahasa. Buat Bapak Ibu yang ingin nanti ada apa namanya attending ini semacam sertifikat, mohon nanti diisi link hadirannya ya. Okay, we continue. Anybody else have any questions? Okay, there's one or couple of questions comes to me directly, Alan. Okay, this is another question. Comparison detection limit if to compare with micro SRF.
Yeah. So we can go back to this slide. So typically, I believe XRF, I know some XRF tools can get into the parts per million range, but I don't believe that XRF are typically in, the parts per billion range. And like you saw with the uranium analysis, that we're able to very easily identify, as well as the corundum, where we can very easily see peaks at single digit parts per million. And we have some experience analyzing trace elements in the hundreds of parts per billion range as well. So verifying those detection limits are in hundreds of parts per billion, then typically its detection limits are lower than those of an XRF or a micro XRF. And once again, X-ray tools struggle with some of these light elements as well. So that's another advantage of kind of the detection capabilities with Massbox. And then it does look like got a few more questions. What year was the LTJ tool manufactured? I'm not sure what LTJ
Rare
refers
earth.
to.
It's a rare earth. It's a abbreviation in Indonesian language. I translated as a rare earth. LTJ is a Logam Tanah Jarang. It's literally a rare earth.
Okay. Yeah, so I guess if he's calling this a rare earth tool, what year was it manufactured? So I mean, we are actively manufacturing these tools, and as I mentioned, just released this next generation in just a couple of months ago. So far, we are also new to international expansion. We have one tool in Asia, one tool in Europe, one tool in Australia, and then the rest of our tools have been adopted by customers here in the US. But we do have distribution partners like PT Lab Systematic, as well as distribution partners around the globe that have started relationships with us and are representing this product to customers. And then specifically on the warranty, so here in the US, we do a 1-year warranty. Of course, that will be up to our distribution partner, PT Labs Systematic, in terms of what sort of warranty they want to offer. But yes, that's how we typically suggest doing it, as a 1-year warranty, and then the opportunity to purchase the service contract to make sure that all of the consumables and all of the preventative maintenance and all of that work is covered.
Okay. Thanks, Alan. Anybody else? There's a question I would like to ask just now. Come to my chat box. For the laser ablation, when you first shoot for the laser ablation, and would it be any potential ionization at this stage before you shoot with a second laser?
Any potential ionization was the question?
Yeah. For the
Um,
Yeah, because you shoot twice, right, with the laser. First for the ablation,
mhm.
and the second laser for the ionization. For the first stage for the laser ablation, would it be any potential ionization? It's just of interest, because what I know, when I work with TOF MS last time, we just use one laser to ionize the sample. But my sample was organic, usually for peptides or protein. Yeah.
Interesting.
Unlike what you do now for the elements. Yeah.
Yeah. So were you using like a MALDI technique
Yeah,
then?
we use multi. Yeah.
Gotcha. Yeah. So when the laser ablation, so I guess first of all, we are tuning our laser to ablate rather than desorb. So if we were doing desorption, which is what MALDI does, then we would keep the molecules intact. So that is a little bit of a different technique. And so we have designed this to be very much a mechanical process so that it is not, creating thermal effects or any sort of ionization. There is a bit of temporal plasma that is created in the ablation process. And so what happens is, after the ablation laser fires, we wait, I think, a microsecond. We wait a little bit of time so that
Right.
plasma can dissipate. And then when we do the ionization step, then we're targeting the neutral particles that are created. So our goal is to, let any sort of plasma or any, potential desorption or any of those sort of challenges, let them go away, and then use the secondary laser to create the ions. And once that process has happened, then we turn on the voltage fields that then send those charged particles to our detector. So yes, it is possible that there is some ionization, that there is some plasma created, but we don't start interacting with those charged particles until the secondary laser has fired.
Right. Okay. Okay. Because yeah. Okay. It's completely different. Because mine, well, based on my background, well, I do well when I did multi-TOF, yeah,
Mhm.
and it's just like first laser is already ionization happens, then you just and the ion just go to the mass spec directly. All right.
Mhm.
Okay. Good to know that we have a new
Yes,
technology.
so it's similar, but yes, different. It's a different process to be
Right.
optimizing for ablation
Okay.
and elemental analysis than
Right.
desorption and keeping molecules together.
Yeah.
Mhm.
Do you need to do some kind of optimization before for the ablation and the ionization before we really do the analysis?
Yes, so we do have like a recommended practice to determine the appropriate laser power to for a given material. So there is a little bit of
Right.
kind of
Yeah.
optimization and tuning.
Yeah.
In fact, it might be nice for me to show this video, which is just the user interface video. Let's see if I can get it to
Okay.
play. Yeah. So this is a user interface video that, our system was designed to be very intuitive and to prompt the user through the process of setting up an analysis without, having a lot of mass spec experience. And so you can see what it's like to the scanner takes an image of the sample tray. The user then defines what sort of samples they've put in. So if we have a standard 6x5 sample holder, then all of those
Mm.
samples get populated and we just have to name them. And so then right here is where we change the laser power. So essentially we change how much the laser attenuates, and that is
Right.
optimized for a given material type. So materials that are very soft, we don't require as much material. A lot of geologic samples, we often need to use a lot of laser power to effectively ablate and break down minerals. You can see how the user is now setting up one of those raster areas. So being able to change the size of the analysis, how many repeats, meaning how many layers you're doing. And then the software tells you how much time that's going to take as well. So now you can see how the user is setting up the same analysis across multiple samples. So if you were doing like a routine analysis across multiple, sediment samples or multiple samples of the same type, you could very easily copy that process. And then this is showing how we would do a spot dwell. So we would do that spot dwell in order to verify, what sort of laser power is giving us a good signal. So I think that may be kind of what you're referring to in terms of the optimization. But now, now that the user has set up all of those analyses, we push start and we immediately see mass spectra. So as soon as the lasers start firing, we start seeing the mass spectra. This user doesn't have the isotopes turned on, so you don't see all the peaks labeled. But once the analysis is done, then you would see that the software would isotopically verify and label the lithium that you saw in at 6 and 7, and then the lead up at 208, and then the tin that was showed at 121. So yeah, that's just kind of gives you a sense of the workflow of setting up samples and what
Right.
the user can change.
Okay. Wow. Cool. Then the next is how much sample that we need, because it's really interesting. Last time when I used multi-TOF, we just like use the multi plate. Then you just like just pipette the sample to the spot, and you just wait till it dries. Yeah.
Mhm.
Do you is it similar, or it's different way to prepare your sample, then how much sample that you need
Yeah,
for
so
that?
the advantage with this is that, the M in MALDI stands for matrix assisted.
Matrix,
So we don't
yes.
have to do the matrix assisted part. So these are what you're looking at here. These are some pelletized powders. That's a common sample prep technique for us. These are like 13 millimeter sample sizes. But if we go back to, the zircon grain example, I mean, these are only a couple hundred microns across. We can analyze very small samples because our spot size goes down to 5 microns. So, we can analyze single grains of material as long as those grains are in that micron range. So we can analyze very small samples, or as I mentioned, also very large samples. So this audience may be interested in, seeing that we can also analyze a whole core sample. So this was a core that had been cut in half and just laid into the sample chamber, and we analyzed that flat part of the core, and we're able to see how copper was distributed and show the customer that copper was actually not distributed in veins. It was actually kind of discretely distributed throughout the sample. So yes, a lot of versatility. We can do big samples. We can do small samples.
Okay. Thank you, Ellen. Thank you. That's
Mhm.
really, really interesting. There's a question from a raised hand from Yuhelda. Mr. Yuhelda, you can just
Yeah,
ask question.
I just
Please.
want to know. We used to work with the sediment samples from marine, from the sea. Is it the salt content of the sediment will influence the equipment? Thank you.
No, salt content should not impact it. The only thing that would impact it would be the moisture. So, because we are pumping our samples down to vacuum to analyze them, anytime we do have samples with a lot of moisture, then they can take a long time to get down to vacuum. So in that case, we would recommend doing like a dehydration or a baking session, where essentially you're, putting them in an oven or putting them in something to bake out that moisture and then put them in the mass box. So it's not salt, it's just, yeah, any sort of moisture or high gas content that could potentially off gas while the system is pumping down to vacuum.
Okay, thank you.
Mhm.
Next question, is it possible? Okay. Uh, yeah, when we examine samples, there is maybe I said, for example, yeah, good content of the sample, because I'm doing research on that. We have problem with the homogenization of the samples. We took from another part, and then they have more of higher content, but the other part is flowing low content. Is it we need to something like mix up, or to mix the to represent the whole of the sample? Is it, or how to prepare the samples to make the no problem with homogenization? Thank you.
Yeah. So are you asking about like, because this is a spatial technique, like if a sample is not homogenized, then it will pick up on the sort of the spatial elemental changes? Is that kind of what you're asking about?
I think it is.
Okay. Yeah. So, it's a good question because, there is an advantage to digesting samples in acid because it just, it takes away any sort of heterogeneity and you just get one number for a bulk analysis. I will share this example of, this is a pelletized reference material that's a, copper ore with high amounts of iron and sulfur in it. But what we found when we analyzed this ore reference material, we saw some pretty distinct heterogeneity in it. And you can see how these areas where there's relatively low iron correspond with these areas of relatively high sulfur, molybdenum, and arsenic, suggesting that you've got these molybdenum and arsenic sulfides that were distributed within this ore sample that, because they had only done, XRF with a bulk technique, they didn't realize how these things were, that there were these, sulfides, agglomerations. So yes, we can pick up on spatial heterogeneity, and we have to be sure that we are analyzing a large enough area in order to get a bulk representation of the sample. So, for example, we have a customer that makes powders for 3D printing, and they put ceramic particles in their metals. And so they have to analyze, they can't just do a single spot and get the correct answer because they have a very heterogeneous powder. So they have to do, large, millimeter scale scans on their powder in order to accurately sample all of the metal and the ceramic particles and get a good bulk representation. So I guess the short answer is that we can get accurate bulk elemental analysis. You don't necessarily have to do a lot of homogenization. We can just scan a large enough area and make sure we are sampling enough of the material to get a good bulk composition. And we have a lot of experience doing that, of analyzing heterogeneous materials and verifying that we get the same results as that of ICP mass spec. And so we can, support your team on developing that method.
Okay, thank you. How many grams required to milligrams maybe? Yeah.
Yeah, so we typically ask a customer for about 10 grams
Okay.
of material just so we have enough material to work with to test and try different sample prep methods. But yeah, we can use as a very little amount of material and just use like a carbon tab or something that you're used to for SEM-EDS, and use a very little amount of material and just make sure we're hitting the grains.
Is it the result directly can be seen maybe after you make a examination from the sample? The result can be seen directly.
Yes, the result
Okay,
can
okay,
can be seen directly. Yeah.
okay. Okay, thank you.
Yep.
Thank you, Mr. Yuhelda. Hopefully it answered your questions. And there's a question in a chat box. For forensic application, which one do you suggest? LALI or micro XRF?
Yeah, I think it depends. So, there's always going to be advantages and trade-offs to different techniques. Um, I am not very familiar with forensics applications, so it really all depends. So, for example, nuclear forensics, LALI might be more advantageous because of its isotope ratio analysis and the fact that, we could look at the different isotopes of uranium and verify if something is enriched or not. So, for some forensics applications, Massbox can be very advantageous for, the gemology forensic applications, determining where gems come from. Sometimes the detection limits may be lower than those of XRF, or if you need to measure beryllium, for example, like we saw in the gemstones, that would be challenging to do with XRF, so LALI would be better. So it all just depends on, what application, what material are you testing, and what elements do you need to detect, and what detection limits do you need to detect them?
Okay. Okay. Anybody else? Maybe another one or two or three last questions. Okay. There's one question come to my
One more
inbox.
question, please.
Yeah.
Yeah. Is it suppose we buy the equipment? Is it also provide the after sales service? Thank you.
After sales service, ya Pak.
Yeah, yeah.
Yeah. What about after sales service, Ellen?
Sorry, what was that?
He was asking about the after sales service.
Mhm. About service. Yeah, so our partner, our Indonesian
Yeah.
partner, would support you and your customer as a customer. So we would rely on them, and then we provide support, obviously, from the US and training in terms of the service and everything. So yes, I would defer to your local representatives about the specifics on that. But yes, you would have local service people in Indonesia, and they would be trained by our team in the US.
Thank you.
Okay, I think there's a question from coming into my chat box. For the elemental mapping, do you use special software to get the image? Because as we all know that when we do analysis with mass spec, you just only have the spectra, right? Yeah. Then how to get the image for the mapping?
Yeah. So the maps that I was showing, I mean, these are in our software. Once you saw the user interface video where you would be able to see your sample from the scanner in the software, you would set up the elemental map, and then once it had been acquired, then you would just click on that area, and then all of these maps you would be able to change the maps and click on the different elements and see them pop up. So all of the elemental maps are viewable in the software. If you're asking about like a micro camera image, we do also have a micro camera that you can zoom into on a sample if you do have micro features to observe. It's certainly not the same power as something like a SEM EDS, but it does allow you to identify, for example, one of these grains and make sure that you're setting up your analysis on that grain. So we do have capabilities to visualize the elemental maps on the sample in our software. And then if you needed something higher resolution, then you could correlate that with something that you get from an optical microscopy technique.
So it's all included in the same in one package, isn't it, for the image?
All of these maps are included in our software. Yes.
Okay. Yeah, that's good to know. That's good to know.
Mhm.
All right. Anybody else who has any questions?
Maybe I can give something a suggestion, because I saw in the picture there is no scale bar. I think better you put some sweet scale bar there, so I can measure directly the size of the mineral. Thank you.
Yeah, it's down here in the bottom right, but you're right, it's not on every
Okay, I
picture.
didn't see it on the right side. Yeah, right. No, yeah, right
Yes.
corner. Okay.
Yeah.
Thank you. Sorry, you didn't see.
Yeah, so this is the
Okay.
6 millimeter scale.
Okay. Is it directly from US? Yeah. Your bro. I mean, this your time. What time now? Yeah, 10 o'clock.
9 o'clock, yes.
Indonesia in 10 in the morning. Okay, thank you, sir.
Okay. One last questions. One last questions.
These have been great questions, so thank you again for your time and the good question, time and interest.
We afraid we disturb your sleeping time.
It is my bedtime, you're right.
Yeah.
Okay.
Okay, if there is no other question, I think I would like to finish our session here. And yeah, thank you very much for everybody. Thank you very much for your time. Thank you very much, Ellen, for your time. That as it's mentioned that it is your bedtime now. It's really hard for you maybe to stay awake. Yeah, but yeah, it's really good
Pakai
information,
pantun, Pak.
and it's really useful for us, and hopefully we can follow up from this point to move forward, and yeah, if there is if there is any other question comes later, then I would like to pass it to you, and yeah, then we continue from here.
That sounds
Okay.
great.
Yeah, thank you very much, Ellen. Thank you very much, everybody. With this, I end this session and this webinar. Thank you
Thank
again.
you, Alan. Thank you, Bapak.
Thank you so much.
Thank
Have a good
you.
day.
Yeah.
You too.